This is Analysis of Time Series, Chapter 4, Linear Time Series Models and the Algebra of ARMA Models. So one of the nice things about ARMA models is that a lot of things can be calculated for them, but we have to learn how to do that. So one of the main tools for calculating with ARMA models is to see that ARMA models can be written as something called a stationary causal linear process. So the first thing we're going to do is define that and then develop some formula for the general autocovariance expression for a linear process, and then see how that can be used for ARMA models. And then we're going to move into writing ARMA models using the Backshift operator, which is a nice little abstraction, but once you get used to it, it gives really compact ways to write down ARMA models, and compact notation helps you calculate things. And so we'll write the general ARMA model in Backshift operator notation, and that'll let us talk about causal invertible ARMA models, and then we'll move on to an example. Okay, so a stationary causal linear process is a time series model that can be written in the following form, which I'm calling model M7. You can see, I won't try to read this out. So yn is some mean mu plus some function of lags of the white noise process. The lags here are called G0, well, the coefficients are G0, G1, G2, and so on. And when we write it like this, we don't need to define any initial values, but we do need a doubly infinite noise process going off to -infinity and then going up to infinity to define yn as it increases. And this looks a little bit like a moving average model, you should notice, except that it goes off to infinity. Now, let's think of the term stationary causal linear process. Well, we've defined stationary, so let's think what stationary means in this particular context. So, let's first of all note that our model M7 is a shift invariant function of the white noise process epsilon n. And we recall that shift invariance and stationarity are essentially the same thing, but weak stationarity is shift invariance of the mean and covariance, and strict stationarity is shift invariance of all distributions. So recall the definition of white noise, epsilon n is weak stationary by definition. And this means that yn is always weak stationary. And then if the white noise happens to be also strict stationary, so is yn. I haven't quite, and this doesn't look like a very firm proof, but it's probably an intuitive argument. Oftentimes with time series, you try to make an intuitive argument, and if you want to kind of really nail down a proof, if you're so inclined, you can try and do that. But our main goal is to understand what's going on. So that's what stationary means in the stationary causal linear model. Causal has a meaning here. Epsilon n's a causal driver of yn in the sense that the value of yn depends only on noise process values already determined by time n. So yn depends on epsilon n minus 1, epsilon n minus 2, and so on. But yn's not allowed to depend on future values of epsilon n. And so this matches a requirement that cause must precede effect, which is a very kind of classic requirement of causation, such as in the Bradford Hill criteria. Linearity is also something we have to think of what it means. Linearity refers to the fact that yn is what's called a linear function of epsilon n. So it's a linear combination of the white noises. Now we can do a little bit of algebra with covariances to find the autocovariance for a linear process. It's certainly weak stationary, so the autocovariance only depends on the lag. So we write it as gamma h is the covariance of yn plus h. And if we write out what yn and yn plus h is, these are two sums over the white noise. That's in equation 2. Now, if we can move covariance through summation, then we can do that. That's what I've done algebraically to move from 2 to 3. And then we take constants outside covariance in the familiar way. And then because epsilon n is white noise, to get from 3 to 4, we're using the fact that the only non-zero term is when n minus j and n minus h plus k are the same. And when they are the same, you get a contribution sigma squared. Every other term in the double sum drops out, so you get a single sum. So we can see, and depending on the g's, this sum might be finite, it might be infinite. If the infinite sum is finite, then you say the sum exists. Okay, so let's think a little bit more about whether it's really legitimate to move the summation through the covariance. Now, when you have finite sums, we know that the covariance of a double sum is the double sum of the covariances. For infinite sums, this is just not always the case. Now, in this course, we're not going to focus on interchange issues, but you should at least be aware that there is an issue that could, in principle, be checked. And a standard way to check this interchange is to require a stronger condition that the GJs are absolutely summable, but we're not going to get into that particular detail. It won't be very relevant for what we're trying to do. Okay. So we've seen that an MAQ model is an example of a stationary causal linear process. It's one where beyond some point, all the GJs are 0. And so as I just mentioned earlier, if you look at that general equation defining the stationary causal linear process, it looks like an MA infinity model. That would be a reasonable name for it, and that's something it's often called. Okay, so let's see what a stationary causal linear model representing the AR1 looks like. It's actually interesting. If you write down the defining model for the AR1, you can actually write a causal solution and a non-causal solution. And it's very natural to think of the causal solution because it's probably the one you have in mind when you're thinking of an AR1. Anyway, let's see what they are. M8 is the stochastic difference equation defining the AR1 model. We've seen that before. And M8.1 is an instance of an MA infinity representation. That's the same as a stationary causal linear representation that I claim satisfies the difference equation M8. And then M8.2 is another slightly stranger looking thing where Yn sums over future noises. And I guess the first thing we really should do is just do the algebra to check that M8.1 really does solve the AR1 equation M8. Let's say for M8.1, if we want to calculate if we want to calculate the difference equation coming from M8.1, Yn by definition is the sum from j is 0 to infinity of phi to the j epsilon n minus j. And what I'm going to do is I'm going to take epsilon n out of that sum. Epsilon n is the first term of that sum, the term when j is 0. And then I'm going to see all the terms I have left. I'm also going to take a phi out of the sum. And the remaining terms in the sum are just j is 1 to infinity, because I've taken out the j is 0 term. And I've taken out a phi, so I have phi to the j minus 1. And I have an epsilon n minus j. And then what I can do for this sum here, I can rewrite it as a sum from 0 to infinity rather than a sum from 1 to infinity. And that gives me epsilon n plus phi times this. Maybe I should change the letter just to make it clear. K is 0 to infinity of phi to the k epsilon to the n minus 1 minus k. This is formally putting k equals j minus 1. Okay, and then I can recognize that as epsilon n plus phi times yn minus 1. This is assuming M8.1 holds, which then satisfies M8. And then I can do the same thing for M8.2. I'm not going to do that for you right now. I'll just say similarly for M8.2. Okay, so that's just some algebra to check that this MA infinity representation of an AR1 really does work. Now, it's nice to have this representation. Particularly, we have this nice formula for the covariance of an MA infinity process. And now we have an MA infinity representation of AR1. We can use that as a way to calculate the covariance of the AR1. Okay. But let's first of all just think about this fact that we have a causal and a non-causal solution to the AR1 difference equation. Now, whenever you have an infinite sum, you can't quite be sure it converges. And so here's a kind of curious thing. If you take M8.1, if we want to calculate the variance of yn, then it's a sum of independent noise terms times phi. So we get the variance of the sum is the sum of the variances. And we have to square the constant. And we get the variance of the white noise sigma. And this is a geometric sum. Which converges when the absolute value of phi is less than 1, right? That's a very well-known mathematical result summing the geometric series. When we have M8.2, which was the non-causal solution to the AR1 model, something funny happens. If you look at it, following the same argument, you have convergence when the absolute value of phi is greater than 1. And that's probably not what you're really thinking of when you have an AR1. You're probably thinking that phi is going to be less than 1. And that's one of the reasons why you naturally think of the causal solution, which is then convergent. Okay, so now we're just going to go through the calculation of using the MA infinity representation to compute the autocovariance of an AR1. And this will give you some feeling that maybe this MA infinity representation is useful for other ARMA models, but we're just going to do this simple case. So we have the MA infinity representation. Yn is the sum from j is 0 to infinity of phi j epsilon to the n minus j, and this is the MA infinity representation of the AR1 model. And then we have gamma h, which is sigma squared. The sum from j is 0 to infinity, gj, gj plus h. And this is the covariance formula for the general stationary linear model, the MA infinity model. And then if I calculate what this is sigma squared times the sum from j is 0 to infinity of phi to the j times phi to the j plus h. And then I take j to the h out and I get sigma squared. I take phi to the h out. And then I have the sum from j is 0 to infinity of phi to the 2j. And that's a geometric sum. I know how to do that. So I get sigma squared phi to the h over 1 minus phi squared. Now, somewhere I've assumed h is non-negative. I think it's in this step here. Okay, and then by symmetry, a very similar calculation works when H is negative. Okay. Now we're going to get into the backshift operator and the related difference operator. So the backshift operator, often called B and sometimes called the lag operator and therefore sometimes called L, is given by something byn is yn minus 1. And the thing that requires a little bit of thought here is that this is really operating on a whole series. You have to think not just of one yn, but all the yns. So it's the series you get when essentially you relabel time. So yn in 1, once you shift it, becomes yn minus 1. Once you've defined that, you can then define the difference operator. The difference of a time series is usually the one lag temporal difference. That's what we just say difference, and we mean one lag temporal difference. So the difference at time n, which is often written delta yn, is yn minus 1. It's the increase in yn over yn minus 1. And we can write the difference using the backshift operator formally as delta is 1 minus b, where we just assume that we can algebraically use the backshift operator just like any other kind of, just like multiplying by a matrix or a constant or something. It's a linear operator. So we can write 1 minus b of yn, and we can distribute that out, and we get 1 times yn is yn, because 1's the multiplicative identity, and minus byn is minus yn minus 1. And so then you can play with these backshift operators and difference operators more. What does b squared mean? B squared means doing b and then b again, and so that's the shifting time by 2. We can also take a second difference, delta squared yn, and again, we just use the fact that algebraically these backshift operators just behave like other numbers, and so we can delta squared, delta is 1 minus b, so delta squared should be 1 minus b times 1 minus b, which is 1 minus 2b plus b squared. And then when we apply that to yn, we get yn minus 2yn minus 1 plus yn minus 2 in equation 10 there. And so we can think what are the algebraic rules for the backshift operator? And an important one is that it's linear. So if I do the backshift operator on a constant times xn, then I can take the constant outside. If I do the backshift operator on a sum, that's the sum of the backshift operators. And so 11 gives you that general linearity property. B of alpha xn plus beta yn is alpha xn minus 1 plus beta yn minus 1. Okay. And so what we've seen here, and what we're going to use extensively, is that backshift operators and their powers can be added, multiplied by each other, multiplied by a scalar, and they follow the same rules as the algebra of polynomial functions. That sounds very much like abstract math, and it is a little bit of an abstraction. But in practice, it just means they behave like we expect things to behave. In particular, they have this distributive rule that we've already used, that you can distribute alpha plus beta b through yn, and you get alpha yn plus beta yn minus 1. One of the nice things about backshift operators is that mathematical properties we know about polynomials can be used to work with backshift operators. And again, you may not have thought much about the mathematical properties of polynomials for a while. And so it's kind of fun to see that they become useful for time series analysis. Okay, so let's first write the ARMA and linear process model equations in terms of polynomials in the backshift operator. And here's a polynomial phi of x, 1 minus phi1x minus phi2x minus phi p x to the p. It's an order p polynomial. It's maybe not the first polynomial you would have thought of. Note the signs. The first coefficient is 1, and the coefficients of higher powers of x to the p have that negative sign there. That's a little bit arbitrary, but it's needed to make everything match up the usual way of writing an ARP model. In particular, if we rewrite the ARP model we had in equation M1 by putting all the y's on the left, we get equation 13 here. And this is where the negative signs in the polynomial phi of x come from, because we decided when we wrote M1, we put yn on the left and all the other lags on the right. And now we're moving it all to the left. So we get some negative signs there. And when you look at 13, you see that the left-hand side can just be written as phi of b formally, and so you can write it as phi of b yn equals epsilon n, and that's a very compact way to write 13. We're going to call that M1 prime. It's equivalent to M1, just written in the backshift operator. And that's the end of part 1. We're going to be back with part 2 to do more with this stuff.